Take it away, Norm.
So we're doing the NISQ algorithm section, and we have Matteo, I'm going to butcher his last name, actually I'll skip it, who is a postdoctoral researcher at Stanford, who's going to be talking about non-equilibrium physics of matter on NISQ hardware. As I said, he's a postdoc at Stanford, where he's doing research at the interface of quantum information and condensed matter theory with Vedika Kanami's group. He got his PhD from Princeton in 2019. And prior to that, he was an undergraduate at the University of Pisa, where he worked on quantum information. And he will start as an assistant professor in 2023 at UT Austin. So quick introduction for Matteo. Can you hear us, Matteo?
Yes, can you hear me?
Yes, you sound fine.
Great.
Can people on Zoom hear us? I'm going to assume yes. Could somebody say yes or no?
Yes.
All right, thank you. So I think we're ready to get started, and Matteo, you can take it away.
Excellent. Thank you so much for the introduction. I was really hoping to be there in person, but unfortunately, I may have gotten COVID or not. Tests are unclear, but anyway, I've had to cancel my travel plans. So anyway, I'm going to talk about some of these recent works in collaboration with the Google Quantum AI group on realizing and demonstrating non-equilibrium phases of matter on NISQ hardware. So this particular audience doesn't need any real introduction to the concept of NISQ, but just to set the stage, I'm going to give this very overview. NISQ stands for noisy intermediate scale quantum, and by intermediate scale we mean some number of qubits that's in the tens to hundreds, perhaps thousands. And noisy stands for the fact that the control is imperfect, and there are error rates on the order of 1% per operation. So with these parameters, we're still not there in terms of fault-tolerant computing. So we're not going to factor large integers with these devices or anything like that. But even at this stage, all of these platforms, ranging from superconducting qubits to trapped ions, neutral atoms, and other emerging technologies, are already extremely interesting condensed matter laboratory systems. And that's in the sense that they are systems of many interacting degrees of freedom that have capabilities for control and measurement that are much beyond or different from what is normally possible on, say, a sample of semiconductor or a more familiar solid state system, for example. So the question, from the computer science perspective, of course, is what quantum algorithms can we realize on these devices, and what interesting questions can we answer? But from a condensed matter perspective, there is a question that arises of what physical phenomena can we realize or simulate or investigate on these kinds of extremely engineered and controlled condensed matter systems. And as you see, this kind of blurs the line between what is a quantum simulation, as we heard in this morning's talk, and what is a proper condensed matter experiment. So this is an interesting development of this NISQ era, I think. So to get at this question from the point of view that I'm going to take for this talk, I have to introduce, start from the basics and introduce the concept of quantum thermalization and how it relates to quantum entanglement. So let's consider an isolated quantum many-body system. We have some collection of qubits, for example, that are, we imagine to be perfectly isolated from their environment, so they evolve unitarily. And let's consider a subsystem of contiguous degrees of freedom, let's call it A, that evolves in conjunction with the rest of the system that we can call B. And the question is, how do we recover our expectations from thermodynamics? So if we initialize this system in some simple state, how do we recover the irreversibility of thermodynamics and the approach to thermal equilibrium? This is at first glance a bit counterintuitive, because thermodynamics has this concept of irreversibility built in, and quantum dynamics for an isolated system is completely reversible, and it's also linear, so we don't have dynamical chaos in the same way that we do in classical dynamics. So the key to this puzzle is given by quantum entanglement. So as our system evolves unitarily, quantum correlations and entanglement build up between the degrees of freedom in A and the ones in B. And as an extensive amount of entanglement is generated, the reduced density matrix of A, so the state we obtain if we discard all the degrees of freedom that are in B, can become described by a thermal ensemble. So this thermal density matrix at a suitable temperature. And so even though there's no irreversibility at the level of creating or destroying information, we effectively gain this irreversibility from the fact that information flows from local degrees of freedom into global or highly degrees of freedom that inhabit the entire system. And this phenomenon that of information spreading from small operators into big operators is known as scrambling, and it can be investigated in quantum circuits. So this is where this connects to quantum algorithms and digital simulation, because of course quantum circuits are the language and the framework for all of these topics. But they're also powerful toy models for studying more general kinds of quantum dynamics, because they essentially strip down all of the complexities that you might have in a Hamiltonian evolution into something that only retains locality and unitarity, that are the very, very basic foundational constraints of a quantum evolution. So, within these models, one can study how, for example, if we initialize some quantum information in a local degree of freedom, over time, this becomes spread out and scrambled over the entire system. And the fact that these models connect to experimentally relevant models of digital quantum simulation can be leveraged to really explore this. And as has been done, for example, in this recent work by the Google Quantum AI group on information scrambling as measured on their Sycamore chip. So for this talk, I'm going to take a different perspective, which is instead of trying to learn universal aspects of the approach towards equilibrium, so let's say we initialize a simple state somewhere in our schematic state space and we watch it evolve over time and approach some kind of equilibrium distribution, we want to ask a different question, which is, can we find or measure universal properties not in the approach to equilibrium, but in late-time states that altogether evade equilibration? So is it possible to have dynamics that, for in principle asymptotically long times, never converge to an equilibrium distribution, but rather maintain some interesting kinds of correlations, long-range order, etc., in the state, which are the kinds of things that we are normally interested in condensed matter. So here, the first problem that one runs into is this kind of growth of entanglement over time that generically arises in interacting many-body systems. So precisely as a consequence of this unconstrained growth of entanglement, it would seem that the answer to this question is negative, because as entanglement grows without bound, we eventually saturate towards a maximum entropy state, which is our only fixed point. And once that happens, there's no hope of having interesting correlations in our state, essentially. And this is closely related to the problem of barren plateaus in variational quantum algorithms, where a similar thing happens, where your parametrized quantum circuit can, explore a fraction of the Hilbert space that basically amounts to equilibrium, thermalized states that where all the expectation values become extremely small, and basically this inhibits your ability of computing gradients and carrying through these algorithms. So here we have a very similar, essentially the same phenomenon, but we view it from the perspective of stabilizing interesting correlations in our late-time states in the language of condensed matter physics. And the challenge is, how can we potentially avoid this ultimate heat death and have such interesting correlations in late-time states? And there's different paradigms that have been proposed for achieving this in various settings, but so the plan for the rest of this talk will be to review one of these paradigms, which is eigenstate order as defined within the paradigm of many-body localization. So that'll be the first part, and I'll in particular emphasize the paradigmatic example of discrete time crystals. And then I'll argue for why this phenomenon is a very natural fit for near-term simulation on NISQ devices. And finally, I'll move on to the experimental implementation on Google's Sycamore chip, where we leverage the strengths of the controllability and the measurement capabilities of this device, and also devise ways for addressing the challenges that are inherently built into the concept of NISQ, so noise and finite size and etc. So that's the broad outline for the talk. Please interrupt me if there are any questions at any point. Okay, so let me start from reviewing thermalization, so this heating process in periodically driven quantum many-body systems that are referred to as Floquet systems. This just means periodically driven. So you have a Hamiltonian that is time-dependent, but with a periodicity given by this period capital T, such that the Hamiltonian returns to itself every upon increasing time by capital T. And we can study these driven systems by looking at the propagator over one period, which is this time-ordered exponential of the integrated Hamiltonian. And we can diagonalize this object much like we would diagonalize a Hamiltonian in a static system. And we can look at its eigenspectrum and try to understand properties of the system at late times. That's because the eigenstates, of course, are steady states and therefore describe some kind of asymptotically late time behavior. So the key difference between a Hamiltonian and this kind of Floquet unitary is that the spectrum of this object is given by phases. Of course, this is a unitary, so the eigenvalues are phases. And from these phases, we can extract in a standard way a so-called quasi-energy. So just taking the log of the phase and normalizing by the period that we can set equal to 1 for convenience later on. And this means that these quasi-energies are similar to energies in a Hamiltonian, but they're defined modulo a frequency, so modulo 2 pi over our period capital T. Therefore, we can imagine these quasi-energies as living on a compact circle rather than a line. And this means that there is no such thing as a low energy or ground state. All these states are kind of interchangeable, living on this circle. And moreover, given that we have a periodic drive that can inject energy into our system, so we can absorb quanta of energy in units of this 2 pi over T, and there is also no sink, there's no sort of cold bath in which to dump any energy or entropy, what we expect is that extremely late time states at extremely late time will have essentially maximized their entropy. So all of these states that are steady states that we have here on the circle will be essentially featureless infinite temperature states, meaning just maximum entropy quantum states. And this is to be compared with the situation in a static Hamiltonian system where the eigenvalues are actually living on a line, and we have ground states and a low energy sector potentially that may exhibit quantum order in the form of symmetry breaking, topological order, and so on. So here we would recover these kinds of high temperature unordered states only at sufficiently high energy in the spectrum. But this doesn't, this distinction is not there in driven systems. So in principle, we expect all the states to be thermal. So a paradigm that was proposed to evade this kind of scenario goes by the name of Eigenstate order. And this was put forward in this paper in 2013 and really only gained kind of mainstream attention a few years later when time crystals were found as sort of particularly interesting instances of this more general paradigm. So let's see, the basic idea is that unlike static systems where you may have ordered states at low energies and then unordered states at high energies, you can have these eigenstate ordered systems where all of the states in the spectrum are ordered and resemble basically ground states of a static Hamiltonian. So this paradigm is enabled or stabilized by many-body localization, which is a phenomenon induced by the presence of strong disorder in the system, where imagine a short-range interacting Hamiltonian system where the couplings are highly random, and this randomness can inhibit transitions between different states in the system, and in doing so, it can prevent thermalization in an isolated system, but even prevent heat absorption in a driven system. So it's possible to have spectra of periodically driven systems where all of the eigenstates on the circle are in fact ordered. And I'm schematically showing them here with some kind of degenerate multiplet to show that these might have symmetry breaking. And so you can have multiplets of symmetry breaking eigenstates that are across the spectrum. Okay. So to make this a little bit more concrete, let me jump into the standard model of time crystals, which is a so-called kicked Ising model. So it's a periodically driven system that you can picture as a classical Ising model with longitudinal fields and ZZ interactions between neighboring qubits. And we're going to think of one-dimensional systems for simplicity. And this evolution is periodically interrupted by a pulse that comes in the x direction. That's parameterized by this coupling strength G. So to take a particularly simple example, let's set this G to be equal to 1. And in that case, what we find is that starting from an arbitrary configuration of up and down spins, what happens is that the the kick with G equals to 1 is a perfect pi rotation of all the spins about the x-axis. Therefore, it flips this configuration into its negation, where up becomes down and down becomes up. And the following classical Ising evolution is completely trivial because all of the bit string states or computational basis states are invariant under this piece. Okay. So as we iterate this sequence, and each period is comprised of a kick and an Ising evolution, we find that each of these bit string states returns to itself only after 2 periods. Okay. So at this stage, this is a completely expected behavior that we've engineered by fine-tuning the coupling. So there's nothing particularly interesting about it. But the really striking phenomenon arises when we introduce strong disorder in these couplings. And in that case, we may stabilize a many-body localized phase where for a value of the Ising kick, which is sufficiently close to 1, sufficiently close to this trivial point, we have a whole region of parameter space where this subharmonic response, so these oscillations at twice the period, persist and remain measurable in these local observables. And that's a really striking phenomenon. And what's particularly striking about it is that it's an intrinsically driven phase that doesn't have an analog in static systems. There's no such behavior in undriven systems. It's also an intrinsically interacting phase that doesn't require dissipation, and it's stable to arbitrary sufficiently weak perturbations. So it's sets it apart from other scenarios where you might encounter period doubling that are more sort of more traditional. And another striking feature that's it's a manifestation of this eigenstate order is that this behavior is not only present in some particular bit string, for example, the polarized or staggered ones or anything like that, but really is expected to be present across the many-body spectrum. So this phase transition from this time crystalline phase into a thermalizing phase really is a spectral phase transition where the entire unitary matrix that represents the Floquet evolution rearranges its spectrum from this kind of thermalizing configuration to this eigenstate order configuration. And I'm going to zoom into this and explain what's going on with those particular eigenvalues next. Okay, so let's, for simplicity, turn off the longitudinal fields that one has normally in the Ising term. And in doing so, we restore an Ising symmetry, this Z2 symmetry that amounts to flipping all of the spins by a sigma x, so negating all of the computational basis states. Okay. In that case, let's say a Hamiltonian system, it's possible to have, for example, ferromagnetism. So the ground states of the Hamiltonian with this Ising symmetry would be, can be Schrodinger cat states of all up plus or minus all down, all 0 plus or minus all 1. So in this eigenstate ordered phase, that can happen not just for the polarized states, but for all the bit strings in your computational basis state. So you can have eigenstates of this Floquet operator that are close to Schrodinger cats composed of arbitrary bit string states like this. And this is an approximation that is weight on, in principle, all of the computational basis states, but it's exponentially decreasing in Hamming distance, if you will, from a particular bit string. So to a first approximation, this is what the eigenstates look like. And an additional wrinkle that is the real signature of time crystals is that these two Schrodinger cats that are the symmetric eigenstates are not degenerate, but they are offset by exactly a pi phase. So they live on antipodal points on this unit circle rather than being nearly degenerate. And this is really important because it has this striking signature in time evolution, starting from an arbitrary computational basis state. So by basically inverting this relationship here, we can write a computational basis state as dominantly a sum of these two eigenvectors with some smaller weight on the others. But from this expression, it's straightforward to see what happens under time evolution, because having these two eigenstates offset by a pi phase means that after a single period of time evolution, they pick up a relative minus sign. And by again inverting this relationship here, we find that this means that we arrive at the negation of our initial bit string state. And in order to return to something close to our initial state, we have to iterate our evolution for 2 periods. So this is the more formal reason for why the phenomenon that I illustrated with this kind of simple trivial example extends to more interesting and less trivial cases. And it's precisely because of this special structure of the spectrum, which gives rise to this spontaneous breaking of discrete time translation symmetry, meaning that your system has a time translation symmetry of capital T, but your observables you might measure have a symmetry of period twice capital T. And the mechanism that gives you this temporal symmetry breaking is inextricably connected to spatial symmetry breaking, because the two eigenstates that are separated by pi are actually symmetry breaking eigenstates for some symmetry you had in the system that in a Hamiltonian would give you say something like ferromagnetism, so a spatial pattern of symmetry breaking. And therefore these linked patterns of symmetry breaking in space and time are sometimes referred to spatial temporal order. And again, I want to emphasize that in this example, I put in an explicit Ising symmetry in the problem, but that is in fact not necessary. So we can restore the longitudinal fields in our Ising Hamiltonian, for example, explicitly break this manifest Ising symmetry, and the same phenomenology should arise for sufficiently weak perturbations. And that's because of essentially the emergence of an Ising symmetry that wasn't there to begin with. That's the lightning overview of time crystals, inevitably quite incomplete. So I'm sorry about that, but it would be a whole other talk. So let me instead jump to why this is a good fit for NISQ devices. And the main, the argument is that, as we've seen this morning in discussing quantum simulation, there is some overhead to simulating some system A with some other system B, right? And even though these quantum simulators are in principle universal, so they could do any evolution that one wants to simulate, in reality, in the NISQ era, we have finite resources in terms of number of qubits and also finite coherence time. So there are tasks that are easier than others, and it's reasonable to focus on tasks that are well suited to near-term exploration. And so two considerations here get us towards simulating these kinds of non-equilibrium phases. The first one is minimizing the number of gates. So minimizing this overhead for compiling, if you will, our task into a quantum circuit. And the argument is that these models, so precisely this kick-Ising model that I showed in particular, is natively trotterized. So there's really no need to compile anything. There exists a quantum circuit with this architecture that exactly implements that periodically driven time evolution. So this is a very good fit. And the second consideration is that if you wanted to simulate some phenomenon that strongly requires on fine-tuned properties of certain couplings, for example, symmetries or conservation laws, etc. That might be problematic with finite control accuracy. And so it's beneficial to have phenomena that not only tolerate, but actually rely on disorder. And that's because in the presence of at least coherent errors, where some coupling in the system is consistently not what you wanted it to be, but somewhat different, well, such a mismatch is actually a feature for disordered systems. So we don't sorry. So we don't have to worry as much about coherent errors in our system. We can, of course, we'll have to contend with incoherent errors and noise, but these two considerations basically taken together strongly suggest non-equilibrium phases in disordered Floquet systems as a good fit for near-term capabilities of NISQ devices. And as you can see from this is really stretching the notion of quantum simulation a bit, because there is really no compilation step. The physics that is being realized in the, let's say, the Sycamore chip, as we'll see, really is, in a quite concrete way, the physics of a discrete time crystal. So there is a legitimate sort of condensed matter point of view of saying that these applications actually realize a given phase rather than simulating it. So this is kind of a metaphysical debate, so it's not really the main point of this talk, but it's an interesting thing to think about, where this distinction lies. So more in a more pragmatic spirit, what are the actual challenges that we have to overcome to potentially realize and demonstrate this physics on a NISQ device? Well, basically, we have to be able to engineer all the control that we need to have the drive, have this quantum circuit mimic the drive that we want to realize. So that's control. Secondly, the intrinsically noisy nature of these devices means that a dynamical phase of matter, so something that's defined only in behavior at late times, is going to be challenging to demonstrate. So we have to devise some way of treating noise that allows us to get to the underlying physics that one would see in the absence of noise. And the fact that these devices have an intermediate scale means that we can't take a thermodynamic limit, which is intrinsically necessary in defining a phase of matter. So we have to be careful with how properties of our system scale with system size and whether they're consistent with the existence of some suitable thermodynamic limit where the phase would be stable. And finally, this defining property of eigenstate order, which is that the entire spectrum exhibits this kind of behavior, is at face value not easy to probe, because the spectrum is, of course, a very big place. And so we'll have to devise some strategies for effectively probing the entire spectrum in some averaged way. So let me start from the beginning. The challenge of realizing this problem on the Sycamore chip is basically tackled in the following way. So we take a one-dimensional subsystem of our two-dimensional chip. 1D is kind of the most natural setting for this physics. And so we're content with a one-dimensional system. And it's also important to keep in mind that this is a one-dimensional subsystem of a 2D grid, where we potentially have other qubits in our proximity that we might couple in at later times. And this will come back to be useful later on. Then the quantizing model that we, that represents the standard model of a Floquet time crystal is given by the sequence of operations shown here. So there is first a kick, so this rotation about the x-axis, which we can implement as a product of single qubit rotations on all the qubits in our chain, followed by this Ising coupling, this ZZ type coupling between neighboring qubits, which we can achieve with controlled Z gates that are within the gate set of Sycamore. And finally, the Z rotations that are necessary for several reasons. One is for breaking the manifest Ising symmetry of this piece of the unitary. Another is to make the model actually interacting, because these two terms taken in isolation would map onto free fermions under a Jordan-Wigner transformation. So we actually, if you want an actual many-body phase, it's important to have this this term which makes the model generally interacting. And composing all of these ingredients, we get a quantum circuit shown here that we can iterate many times. So those are the periods of our driven evolution. And after some number of periods, we can interrupt the dynamics and measure all the qubits in the computational basis and get some bit string states. So here there's a couple considerations. First of all, we set all of these couplings to have large disorder, which is necessary for stabilizing this many-body localized phase. And given that, as we tune this coupling G, we expect a time crystalline phase for a finite chunk of parameter space near this G equals to 1 point. That's the trivial one that I showed earlier, where the system really is kind of trivially oscillating between computational basis states. And we expect some phase transition somewhere, below 1. We'll find it to be somewhere around here. So all of these single qubit operations are very easy to implement on the Sycamore chip. The control phase gates required some engineering developments from the Google team, in particular in terms of being able to realize disorder efficiently. So having these random values be efficiently sampled with each run. So not having to calibrate them one by one, because that would make the problem sort of prohibitively complex. And this has been achieved by developing some on-demand family of control phase gates, where, as a function of various parameters in a pulse sequence on the superconducting qubits, one finds an entire family of these control phase gates, which contain basically this two-qubit interaction Z1, Z2, with a tunable arbitrary angle phi between in the entire range 0 to 2 pi. Basically, this is the plot that most matters. As a function of some microwave pulse strength, you can sweep this angle in the entire circle. So this is what makes this family of disordered models efficiently realizable, basically at the software level at this point. So finally, after this preamble, let's get to some actual data. And this is data obtained by our collaborators at Google, in particular, Xiaomi and Petr Ambrusian. And we're showing here 2 points that are sufficiently deep in the respective phases. So if we set G equals 0.6, for example, we are, we expect to be deep in the thermalizing side. And we can see that the expectation of sigma Z is in fact quickly decaying from plus or minus 1, which is the initial state, the computational basis, to something very close to 0. And this is happening across different disorder instances of the model. Conversely, if we set our value of G to be close to 1, we can see that these oscillations persist for a long time. However, they are decaying, they're damped with some exponential envelope in all of these instances, as you can see. And so the key question is understanding whether this decay is coming from an intrinsic physical phenomenon that's present in the system. So is the system, in fact, thermalizing, even in an ideal limit, or is this a consequence of external decoherence, such that if we could, in principle, turn a dial that sets the noise to 0, would these become asymptotically stable oscillations? And so this is what gets us to the second challenge. Can we try to get at the underlying physics and somehow get rid of the noise? Can we mitigate the effect of noise on this kind of data? So the idea that we pursue is based on a kind of echo protocol that leverages the fact that our intrinsic dynamics, which is unitary, is completely reversible, whereas the noise in the system is incoherent and irreversible. So we can look at this kind of echo circuit where we have a number T of periods of forward evolution, followed by the same number of periods of backwards evolution, which we can achieve by just changing the couplings in our gate set. And again, here it's crucial to have this freedom of choosing couplings at runtime. So having this entire gate set built in is important. And given this echo sequence, you would expect it to take you back to the initial state, right? So for any given choice of computational basis state at t equals to 0, you would expect to go to some complex state and then return to the initial state when the echo sequence is complete. And so this black lines that represent the measurement of this echo sequence correlator should be, in an ideal world, should be identically equal to 1. And so the fact that they are instead decaying is a sharp signature of the fact that there is decoherence. And not only that, but it lets us measure the strength of decoherence in this many-body setting. So importantly, this is, if you look at these black curves, you'll notice that they are different between different points of parameter space. So in the thermalizing side, this curve is decaying more quickly than in the localized side. So this measurement is not just measuring sort of single qubit or 2 qubit noise parameters, but is really sensitive to the interfacing of single qubit noise with many-body dynamics. In essence, what's happening here is that the chaotic dynamics on the thermalizing side is making decoherence more effective at quickly washing out information in some sense. And so with this, we can try to get at the underlying behavior of the system, absent noise, in the following way. So let me make an assumption here, which is often sort of corroborated in practice and is widely used, of depolarizing noise, where after each gate on a single qubit or 2 qubits, there is a depolarizing channel, let's say on a single qubit, which with some probability completely degrades the quantum state at that location, turns it into identity, and with the complementary probability does nothing. So because this noise channel is self-adjoint, we have that the forward and backward evolutions are described by quantum channels that are in fact the adjoints of each other. So this channel phi describes the unitary channel, U sub f, which is conjugation by the unitary, sandwiched in between this depolarizing noise. And whether we're going forward or back is represented by the whether this channel is phi or phi dagger. So what we measure under this noisy echo sequence is the action of the concatenated phi dagger phi channel on the system, basically. And so the measurement of our echo autocorrelator that I'm going to call A0 is basically this object here, which is trace of Z with this time-evolved phi dagger phi acting on Z. And by exploiting the definition of the adjoint of a quantum channel, we can make this channel phi act on its left instead of its right. And we arrive at this conclusion, which is that the quantity A0 that we measure, this black curve that measures the effect of decoherence, is in fact equal to the 2 norm of the Heisenberg picture operator sigma Z at qubit I, evolved at 2 time t. So this is a quantity which would be constant in presence of under unitary evolution, but in the presence of decoherence, it actually decays over time, as shown here. And this gives us a way of taking out the leading effect of decoherence on our original measurement, which is this autocorrelator A, by simply taking this ratio. Because given that our autocorrelator A is just an infinite temperature expectation value trace of Zi of 0, Zi of t, by dividing it out by this A0, we are able to essentially normalize our operator by its norm and ensure that there is no overall decay in the norm here, which is the first order effect of decoherence in some sense. And by doing this, we are somehow accessing, at least in an approximate sense, the response of the system in the absence of decoherence. And also want to emphasize again that this is sensitive to the interplay of sort of local noise with many-body dynamics. So it's a kind of a automatically tailored solution dependent on where you are in the phase diagram. And so how this works in practice is shown here, where again, the top panel is the same data that I showed earlier, and the bottom panels are these ratios of A divided by A naught, which, as you can see, depending on where you are in the phase diagram, either decay very quickly towards 0 or maintain this essentially stable amplitude of oscillation for as far as we can measure. So this is of course, doesn't prove that this oscillation would persist all the way to infinity. This is obviously not something that's possible to measure within finite coherence time, but it is a non-trivial check that other similar-looking physics might actually fail, might actually exhibit some intrinsic decay that's there, even absent noise. So, having addressed the finite time limitation, the twin problem is the limitation of finite size. So we want to be able to somehow study a phase of matter by only using 20 qubits, which is not ideally what you would like to do. You would like to be able to have a thermodynamically large ensemble of degrees of freedom. That is, of course, not cheap or feasible today. And within NISQ limitations, we'll have to find strategies of making the most of a finite number of qubits. So here, a trick one can use when it's not possible to make the system bigger is to simply make it smaller. And doing so in a sort of strategic way, and measure something that should exhibit some expected scaling with the size of the system that points to the stability or instability of the phase you're seeing. So what we'll look at here is this so-called spin glass order parameter, which is nothing but this sum of 2-point correlation functions, Zi, Zj, squared. And the square is important because, it's important because this quantity was used in spin glasses, and the time crystal is a kind of spin glass. And in spin glasses, you have long-range correlations, but with random signs. So a naive average would sort of wash this out by adding up +1s and -1s, and we want to avoid that, therefore, this square. We're also taking some other sort of precautions by removing the edge qubits, which have some edge physics that is very interesting and actually has been studied recently by the Google team again, but it's not the physics we're interested in, which is really a bulk response. So that's why we're taking out the edge qubits. And the spin glass quantity is expected to, because in the localized time crystal, all of these expectations are expected to be of order 1, finite, this overall scaling should be linear in system size. We are adding up essentially L squared finite numbers and dividing by L, therefore this should diverge towards infinity. Conversely, on the thermal side, once the system becomes thermal, any of these expectation values will become exponentially small, and therefore, even by adding up, L squared of them, we're still going to converge towards 0 at late times. So, given these expectations, what does the data actually look like? So what we do here is we start with our chain of maximum length, 20 qubits, and then we sort of make it progressively shorter to 16, 12, and 8 qubits, and we measure the same quantity in each of these cases. And these are curves for the value of this order parameter as a function of G. And as you can see, so I guess some considerations first on because this is intrinsically dynamical, you have to make this measurement at some particular time, and there's no, ideally you would want to wait for an infinitely long time where all the transients have died out, but of course with decoherence you can do that, or your system will have completely decohered. So empirically, sort of an optimum that works well within these constraints is measuring at about 50 to 60 cycles in the problem. And as you can see, at this time, you're already able to resolve the two different trends in the two phases. So in particular, at this value of G that's above the putative transition, you can see that the value of this quantity increases with system size. So these values are increasing here. And on the other hand, below the transition, you can see that if you zoom in quite carefully, you can see that these measurements are actually decreasing with size. And I want to emphasize that this is quite a heroic measurement from our collaborators in the Google team, because these numbers are very small. So you are trying to resolve a small variation in a parameter which is already at the order of 10 to the minus 3. So this requires a lot of shots, and it's a demanding measurement, but it's, I think, very exciting that one can in fact resolve both trends. And this gives you a sort of loose estimate of where this finite size, at least the finite size crossover version of this asymptotic phase transition should be, which is consistent with numerical simulations. And of course, at this level, this, given particularly decoherence time limitations and also the system size limitations, doesn't beat classical algorithms. So we haven't achieved any kind of quantum advantage with this, but I think it's very promising and exciting as a demonstration of finite size analysis of a non-equilibrium phase transition on a NISQ device, which is now starting to become possible for several of these problems. And finally, we've basically, for now, focused on initializing particular bit streams and measuring single qubit expectations, but really we would like to get at something deeper, which is the behavior of the entire spectrum in this problem. And a naive thing you might do is just a brute force sampling of a bunch of bit strings, which our collaborators have done by looking at 500 states, which is a considerable amount of work, but even then is only probing a tiny fraction of the spectrum on 20 qubits, which is already about 1 million states, therefore a fractional percent, right? So that's okay, but of course this is going to get exponentially more demanding as you increase the number of qubits. So it's desirable to somehow have a more scalable alternative to this approach that's taking advantage of some of the capabilities of this device. And the idea that we're going to use is based on the concept of quantum typicality, which is that random vectors in the many-body Hilbert space are, in a specific sense, self-averaging. So each one of them somehow captures the average behavior of the entire Hilbert space. So more specifically, if you take the expectation of any operator O of your choosing on the Hilbert space on one of these random vectors psi, then you'll find the spectrally averaged expectation, so just a trace of O, up to a fluctuation which is exponentially small in the system size. So this is very, very attractive for our purposes because essentially it allows us to, by preparing a single state, of course we have to say how we do so, but preparing a single state, we can get the response of the entire spectrum. Okay, so the way we can prepare such a random state in this experimental platform is by sort of running a state preparation circuit before our actually time periodic Floquet sequence that I described earlier. And we do so by running a circuit with the same architecture, so the same array of controlled Z gates and single qubit rotations, except we make the single qubit rotations spatiotemporally random. So this creates a quantum circuit that scrambles information pretty efficiently, and the level of randomness we need for this purpose is technically a 2 design, and that is achieved at a depth of this random circuit proportional to the number of qubits. So in particular, with 20 qubits on the order of 20 layers will do the trick. And these are numerical simulations where you can see that this relative fluctuation, take some sigma z observable that you want to measure and plot the relative fluctuation on a family of these random states prepared starting from different bit strings filtered through the same random circuit. They'll essentially decay exponentially very quickly, and at the order of 20 cycles will bottom out at the essentially hard random predicted value. So these histograms will contract up to basically a delta function where any one of these states will do the trick and get you the spectrally averaged expectation value. So as I was saying, we can concatenate this state preparation circuit with our time periodic dynamics. But the problem is that we want to measure not just a single sort of one-time function, because that would inevitably have an average of 0. But we want to measure a two-time correlation function. So correlation between the initial value of sigma z and the value of sigma z after some number of periods of this quantizing dynamics. And this is, at first glance, not immediately obvious, because how do you measure a two-time function? But of course, to do this, we can take advantage of the programmability of this device and the fact that we have a 1D chain of qubits that's embedded in a bigger two-dimensional chip. So it's possible to bring in ancillas and couple them into particular places in our system. So the way we can measure this two-time correlation function is through a version of a Hadamard trick, where we bring in an ancilla qubit in a plus x state, so 0 plus 1. And in parallel, we scramble our quantum state here, prepare some state psi. And both before and after our time crystal dynamics, we couple the ancilla to the system with a controlled Z gate. And at the end, we measure the ancilla in the X basis. So now I'm going to go step by step on what this does and why this returns precisely the quantity we want. So basically preparing this ancilla in this up plus down state creates, in some sense, two branches to the time evolution, an up branch and a down branch, which exist in parallel. And we start out like this, right, with the same state psi on both of them. After the first coupling with the ancilla, the controlled Z gate applies a sigma Z only in the branch where the ancilla is down. After this coupling, we have the time periodic dynamics, which attaches u to the t on both sides. It's independent of the branch. And finally, we have another one of these selective controlled interactions, which sticks another sigma z on the down branch. And at this point, we perform a measurement in the x basis on the ancilla, which what it does, because sigma x is off diagonal, it couples up and down. What it does is it takes this inner product between the two branches, this kind of interference phenomenon, and it gives us exactly this, we can recognize here this Heisenberg evolved operator, and finally obtain our two-time correlation function in this way. And finally, by invoking the quantum typicality statement, we can replace this expectation on psi with a spectrally averaged expectation or trace. And so putting it all together, we have data that looks like this. So this is this autocorrelator on one of these random states psi. But we can further enrich this by composing it with the time reversal sequence that allows us to estimate the effect of decoherence. And this works quite nicely. We have this black curve, which again kind of closely matches our decay at late times, and we can take this ratio that gives us oscillations consistent with some finite amplitude for this state, which is implicitly averaging over the entire spectrum. So this is again a non-trivial check that this response is not sort of a fine-tuned behavior of certain states, but really has is present in the entire spectrum, or at least a finite chunk of the spectrum. And this is particularly nice because it's all scalable. So this trick of using random states is only going to get better with increasing the number of qubits. And therefore, this is very appealing for future demonstrations of non-equilibrium phases on potentially larger chips. Okay, so just to wrap it up, I want to take a longish term perspective on the history of this physics that looks back at the past decade and how this falls into context. So time crystals were, I think, initially proposed in quite a different flavor by Frank Wilczek in 2012 as equilibrium systems that somehow break time translation symmetry. And a couple of years later, there was a no-go theorem proven for why this cannot happen under reasonable assumptions in equilibrium. But in 2015, 2016, this idea was actually resurrected in the framework of periodically driven systems by using this idea of eigenstate order that I described earlier. So then there was a first wave of experiments on mainly on analog simulators, on like MB centers or nuclear spins in solids, that exhibited very, very interesting physics, but not quite the eigenstate ordered time crystal that I described here. And this was actually unraveled over a few years by theorists, afterwards, with the discovery of all of these variations of critical or so-called pre-thermal time crystals that are not eigenstate ordered, but share many of the sort of finite time features with them. And then this is where we sort of propose to use the capabilities of NISQ devices to sort of have all of the ingredients that would be needed for a crisp demonstration of this physics. And that's where, both this experiment that I discussed and other simultaneous experiments have come in and are sort of pushing this frontier of investigating non-equilibrium physics on a range of NISQ platforms, from superconducting qubits to trapped ions to nuclear spins and so on. And so I think this is very exciting, and I look forward to seeing where this line of research goes in the future as the technology keeps getting better. So just to recap and to conclude, I've argued that NISQ era technology opens up some new possibilities for quantum many-body physicists and for problems in dynamics and strongly interacting matter that would not be easily accessed on more traditional condensed matter platforms. So in this talk, I've discussed non-equilibrium phases in driven systems and how to realize this eigenstate ordered time crystal in a scalable way. But in the future, I think that there is particularly exciting directions to be explored in the increasing integration of quantum computing capabilities with many-body physics. So here we've used, for example, we've coupled in ancillas, we've performed, the Hadamard trick, or used random circuits to integrate the kinds of things we can measure on a condensed matter system. But there are undoubtedly other very interesting things one can do to either gain a kind of microscopically resolved access to physics that you already independently cared about, or even potentially discover new physics that you didn't know existed. So I think these are all very interesting directions. And I'll conclude here. I have to thank, these are works that were done with many people, and I want to thank in particular Xiaomi and Pejan Rushan at Google, who did the heavy lifting on the experimental work, Kostya Kechezi, who collaborated on the theory side also at Google, Roderick Mosner and Shivaji Sondi on the theory side, and of course Vedika Kemani, who's my postdoc advisor at Stanford. And these are the references for first the theory proposal work and then the experimental work that was recently published. So thank you so much for your attention. I'll be happy to take any questions.
Any questions from the audience? Yes, Pablo.
Hi, Matteo. It's Paolo Poggio from UNM. So I wanted to ask, is there, or do you have a general notion of how hard it is to simulate these, the evolution where you start from a bit string, right? Where you start from a product state, how hard it is to simulate that classically with tensor network, stuff like that? Because I would expect that in the time crystal phase, the system will develop much less entanglement than in the thermalizing phase.
That's exactly right. Yeah. So that's a very good question. That is, of course, a thing that our colleagues at Google are very, very keen on, sort of doing things that are hard to simulate classically. However, that is mainly not the case here. So on the time crystal side, as you are saying, the dynamics is quite efficiently simulable with tensor networks. That's because the eigenstates have only area law entanglement. The dynamics actually achieves volume law entanglement, but does so logarithmically slowly in time. So the bond dimension will grow only polynomially in time. So it's quite efficient. On the thermalizing side, the dynamics are in principle complex, but first of all, it's in 1D. So again, there are lots of tricks you can play. Secondly, yes, there is probably nothing much of substance to observe from this measurement. So truncation of tensor networks probably work acceptably well. What is probably what is complex and an outstanding problem for classical computing as well is the phase transition. So this is hard. It's a topic of ongoing discussion. However, the limitation is somehow the most pressing limitation is time. So it's most important to have a simulation of extremely long times rather than adding a few qubits but having sort of finite coherence. So this kind of method is very unlikely to overcome classical computers, at least as far as we know for now. But so this is where the complexity will be. But of course, if you wanted to have something that is harder to simulate, then 2 dimensions would be you would want to move to this kind of experiment in 2 dimensions. So this is sort of provably hard in the thermalizing side, I guess. And there are interesting pre-thermal time crystals in 2D one could look at, and the transition between that and fast thermalization, for example.
Thank you.
We've got a question online from Young Wang at Oak Ridge about which quantities to measure an average over the entire spectrum. For any one-time observable O of t, even it is not trace zero observable like Z of t. The quantum typicality should give you the expectation value of O of t equals trace u to the n of minus t. Oh, pretty much you highs. Let me just drag this. Just math here.
Yeah, okay. I'm also looking at
Instead of reading a lot of the question, which becomes time independent. Is this correct?
It becomes, yes. So for any one-time observable, you will in fact obtain the trace. So that's why our Z of t will go to 0, and that's not what we care about, right? What we care about is a 2-time correlation, which can have, so we want to probe whether there is local memory of the initial condition at late times, basically. So whether, yeah, maybe we can put it that way. If O of t has finite overlap with O of 0, then you're measuring trace of O of 0 squared, or at least a piece of that, and that can be non-zero.
Right, very good. Thank you.
Yeah.
So I have a follow-up question. Then for the same principle, for the equal time when you verify finite-size effect for the equal time correlator, the trace should be the same at any time. So why do you need to wait until 50 cycles to measure it?
I'm sorry, I kind of got part of the question, but I didn't quite get what measurement you're talking about.
So when you verify the measure spin glass order, the
Spin glass, okay.
yeah, ZIDJ.
Yeah.
Because it's equal time, so the trace cyclic properties, the time evolution shouldn't matter. So you said it's best to measure until 50 cycles.
Yes.
Why so?
I see. So this is perhaps poor notation, but implicitly there is a time dependence in here. So you're measuring, it is equal time, but the state you're measuring it at is time dependent, right? So you're starting from a bit string where clearly in a bit string state, all of these are plus or minus 1, right? So this quantity starts out maximal. And then over time, this can decay to 0, and it does in the thermalizing phase. So it is in fact time dependent, even though I didn't write it here. And
you're measuring in a typical quantum state, the random state. It's like you trace over the spin, all the spin configurations. Then the trace gives you the cyclic properties. The time dependence should be dropped.
Oh, I see. If you did the quantum typicality trick here, this would be time independent. I agree, yes. So if you wanted to do that, you would have to restore Zi of 0, Zj of 0, Zi of t, Zj of t. So again, do a 2-time expectation of this 2-site operator. That would be the analogy.
Okay, thank you.
Yeah, good question, yeah.
I had a quick question. This is Norm. There's been, including the paper you're on, several other experimental papers that have come out, I think all in the last 6 months, maybe, or at least last year. Are there any significant differences between the experiments? Can you just elaborate on any thing that might be important between them?
Right. Great question. So I guess we are Yeah, so essentially, I think once we wrote this down as, okay, here are all the requirements and here are the things to measure, I think that several groups realized that they have the capabilities of doing some of these things or all of them. And so there's been this paper on superconducting qubits where I think it's the largest one on 20 qubits thus far. And it has, this quantum typicality measure, for example, is, as far as I know, the only paper that does it. The paper by the Delft group that came out in Science about the same time uses nuclear spins. So they have a crystal with some chain of nuclear spins that they can isolate, and that's on 9 qubits. The advantage there is that the bare coherence times are very good. So if you're looking at actual times, the Google chip, lives for about a few microseconds, perhaps a millisecond or so. Whereas that experiment, I think, lasts a few seconds, perhaps hundreds of seconds, I'm not sure. But anyway, just the bare time scales are longer, but the number of periods is comparable, perhaps a few hundreds. And it's somewhat less controllable. So the couplings are built in dependent on the position of the atoms. So you can't freely move them around in the same way that you can kind of freely program the values of the couplings. Then there's been other papers looking at slightly different phenomena. So this one on trapped ions looked at a pre-thermal time crystal, which is not exactly the same phenomenon, but it arises from driving a system at high frequency, and it has a finite but long lifetime that you can study. And recently, the Google team put out a paper on looking at Majorana edge modes in an Ising model that is essentially the same that we looked at in this paper, but focusing on a different feature on the edge modes. So these are all kind of different aspects of similar non-equilibrium phenomena. Yeah, these are the ones that come to mind on the spot, but I'm sure there's more.
Thanks. Any other questions? All right, thank you, Matteo.
Thank you so much.
There will be a discussion section in 20 minutes, and we would love if you stick around for that.
Of course.
All right.
Thanks, everyone.
So I think we're